Welcome to Brain Vision.
So we have a beaker with height h, which is 1.520 meters, and on the bottom half of the beaker is some gas, and the top half is liquid mercury. And let's say that the cross-sectional area of a beaker is given by A, and we are asked to find at what temperature the gas will expand enough that half of the liquid nitrogen will leave the cylinder, essentially. So let's start by finding P1 and P2, which is the pressure of the gas before and after this expansion. So P1 is given by this equation. P1 is kind of like buoyancy, right? So P1 is equal to P naught, which is the surrounding pressure, which is the pressure of air, plus the density of mercury times H over 2 times G. And we know H. We can also, it is given the density of mercury, which you can look up, is just 13,593 kilograms per meter cubed. And if you plug everything in, you should find that P1 is equal to 2.02 times 10 to the 5 pascals. Now for P2, we need to remember that our gas is actually not 3/4 H below, but is in fact 1/4 H below the liquid mercury. So we can use the same equation. P2 is equal to P naught plus density of mercury times H over 4 G. And you just find that P2 is equal to 1.52 times 10 to the 5 pascals. Now, if we want to find our temperature for essentially after half the liquid mercury flows out, we can turn to the ideal gas law, right? So PV is equal to nRT. RT. And now let's put numbers on this one so we make it clear which case we're talking about. And let's divide both sides by P2, V2, and nRT2. Now N stays the same because we're not going to gain or lose any moles below the piston, right? So we can cancel that out, cancel R out, and rearrange such that T2 is equal to P2 V2 over P1 V1 times T1. Now we have P1 and P2. V2 and V1 are also quite easy to get, so let's write those out just now. T2 is equal to, well, we know P2, right? We found that 1.52 times 10 to the 5. And V2, saying that the cross-sectional area of the cylinder is A. We know the volume of a cylinder is the area of the base, which is A, times the area of the height, which in our case in 2 I should say, is 3H over 4. 3H over 4. Now for P1, which we have also solved already, we know it's 2.02 times 10 to the 5. And again, our volume is the area of the base times the height, which is H over 2. And this is all times T1, which is just 273 Kelvin. And if you work this out and cancel your A's and you cancel H, you should find that T2 is equal to about 307 Kelvin.